Hello, class. Continue section 8.1, the idea of confidence intervals. Let's do another example or two. So let me pull up some more slides from the book. And again, the book does a good job on this section. So if you are confused and the lectures are a little fuzzy, the book might help as well. And so here are the assumptions that we're doing so far. Got a random sample, and we could use the central limit theorem idea of the mean of any distribution will model a central limit or model a normal distribution given the sample size is greater than 30. And we're also making this assumption, which usually is not the case, but if it is, we can use the z-scores where we know the population standard deviation. We'll show you a different technique when the population standard deviation is not known. But before we do that, let's make sure we got this thing under control, right? So let's go through another example. So here we have a machine that fills cereal boxes and is supposed to put 20 ounces in each box. And we take a random sample of 6 boxes is found to contain a mean of 25.25 ounces of cereal. It is known by past experience that the fills are normally distributed. So remember from the central limit theorem, we can use the central limit theorem if the actual distribution is normal, even with a n value less than 30. And so they give you the population standard deviation of 0.2, and they want to come up with a confidence interval of 90%. So our mean is 20.25. Our n value is 6. And we're going to deal with this confidence interval of 90%. And so the first thing we need to look up is you go back to our table. And here, let me pull it up here and show it to you. So this table will come in handy because all the z-scores we need. So a confidence level of 90% will give us the z-score of 1.645. So that will come in handy for our calculation. A lot of clicks. 1.645 is our z-score associated with that. So the next thing we want to calculate is that margin of error, right? That's what we need. That's the plus or minus aspect over the mean. And so the margin of error will be the z-score, which is 1.645 times square root of n, which is 6. And I forgot to write the standard deviation up here. And the standard deviation was 0.2. So we would do 0.2, get out your calculator, and you would see you would get a number of 0.1348. And so, that didn't look like a 13. There we go. And so basically, the high end would be 20.25 plus 0.1345. And that would be 20.38. And the low end would be 20.25 minus 0.1345. And that looks like that would be 20.12. And again, just do this real quick. And so that would be our 95%. This would be 20.12. Whoops, that's the low end, wrong number. But the big number up top, right? 0.38. And then this would be 20.12. The mean's right in the center here of 20.25. And this is what 90%, right? And so we have 5% on both these tails. And again, that's what we define as the that alpha over 2. Same over here. Okay, so that would be Here's what the slides has for this calculation. I think it's important that you see the little graph as well. Kind of keeps that idea of the symmetry and the 90% where there's 5 on each side, et cetera, with regards to that. So your fancy calculator has a Z interval that you could use to get these directly. I think it's important to first get a good feel for how to do it by hand. And again, these calculations aren't horrible, and it's important to understand where these numbers are coming from. So I'm not going to talk about that. We'll move into some more of the technology a little bit later. So, but there's this idea of the confidence versus the margin of error. And there is a little trade-off. If you have a higher level of confidence, and as the higher level of confidence, then that margin of error aspect needs to get a lot smaller, right? And so if that happens, the best way to do that is to definitely get more samples. That's kind of the rule of thumb. The more samples that you have, because we have division by square root of n, the better off you're going to be in these calculations. And that's what we mean here by sample size. And so the idea here is that if you are going to want a smaller margin of error, the idea is to get a higher n. And so the idea here is that if we let m equal the margin of error that we're looking for, and here's our z-score, right? And so you would look that up. And what value of n do we need given the population standard deviation and to get a valid calculation that would fit into our confidence level? And so basically what you're doing here is you're going to plug these numbers into our equation. So let me just show you one example. And so say like we have a confidence level of 95%. We know the z-score for that is 1.96. And here we're looking for a margin of error of just a half a gram, where we know that the standard deviation of the population is 3 grams. So you just plug all those in. So the z-score here, 1.96, standard deviation of 3, and then the margin of error we want is 0.5. And so what would that mean? Well, we don't know what the mean is, but it'll be 0.5 above the mean and 0.5 below the mean. So if the mean was 10, it would be 10.5 and 9.5. See what I mean? What we mean by that margin of error, plus or minus. And so when you plug that in, you get a number a little bigger than 138. And you always round up to make sure that you're a little bit above your margin of error instead of a little bit below. So that really ends section 8.1. Here are the things that you should know with regard to that. But the main aspect is this idea of calculation of a confidence level, where you're given the z-score and the central limit standard deviation, multiply those together to get what we call the margin of error. So that'll be plus or minus that of the mean. The high end, you add that value. The low end, you subtract that value. So that ends recorded lectures for section 8.1.